Okay, another quick revision on critical angle and total internal reflection. So looking at my notes, okay, I gave you, there was case 1, 2 and 3. So case 1 was when angle incidence is 0 towards a semicircular glass block like this, you just go straight through. Why? Because the angle incidence is 0 degrees. Right, then you slowly increase the angle of incidence. Now it's less than a critical angle. What will happen? Well, as usual, the light ray here goes straight through, but when it hits here, it refracts away from normal, bends away from normal. Okay, same thing, mention what? Okay, bend away, right? Traveling from what? Optically denser to less dense medium, okay, which is air in this case. Okay, glass to air, right? And that causes the speed of light to increase. Speed of light increases. So you always talk about these three things when you explain. So it bends away. So you ask to explain, you write these three things down. Okay, so this is less than critical angle. Okay, in case you have forgotten what is critical angle, okay, all these mediums like glass, water, they have a certain critical angle. So what happens if your happens to be your angle incidence is equal to the critical angle? Now what will happen? It's equal, okay, so you keep increasing this light ray angle until it's equal to the critical angle, okay, so it may be of a certain value. Your light ray will now, it will still come out, but it will refract at what? 90 degrees. So at critical angle, it refracts at 90 degrees. Okay, so only when it's equal, it will refract at 90 degrees. So if you have an eye, you have to look here. The light ray comes here. Okay, there may be a little bit of reflected ray, but most of it will be still reflected out at 90 degrees. So here at 0 degrees, here less than critical angle, here equal to critical angle, and then of course you come to the next point, which is what happens when it's more than critical angle. So if your angle incidence is more than critical angle, so you keep increasing, the light ray does not refract out anywhere here. So you can put your eye anywhere here, you cannot see. So the light ray hits here, it reflects back in here. Okay, so it's a total, we call it total, that means nothing comes out. Okay, total internal reflection. So if this happens to be 70 degrees, this will also be 70 degrees because it's a reflection now. Okay, so this is when it's more than critical angle. Okay, so when you are asked about it, okay, the when or why does it take place, right? You have to always mention the two things. Total internal reflection takes place, okay, when the light ray is traveling from optically denser to less dense medium, right? So it cannot happen from, let's say, air to glass, but only glass to air, right? And the angle of incidence is larger than the critical angle. So now it's larger than critical angle, well, you will have total internal reflection occurring. Okay, so always mention the 2 points. Okay, do not neglect one. Very often students forget to write the first one. Okay, almost nobody forgets to say, oh, total reflection occurs because the angle of incidence now is larger than critical angle. But you also need to mention the first condition, right? There are always two conditions here. Okay, so we talked so much critical angle. I hope you remember how to find use what's the formula of critical angle. N equals 1 over sine C. Okay, that's the good way to remember. Some students prefer this way, but I just prefer it this way myself. C is your critical angle. So if you are given N, the refractive index, you can find critical angle. Okay, and also be flexible that if you are given the critical angle, you also can then find the refractive index. Right, so with the refractive index, I can find my critical angle. Right, then of course the definitions you must remember properly. Okay, you cannot just say total internal reflection is the total reflection of light. You can't say that. Okay, you got to say it properly like this. It's the complete reflection of a light ray inside an optically denser medium at its boundary with an optically less dense medium. And the critical, so this is the definition for total reflection. So in the proper definition of critical angle, okay, when the angle of incidence in an optically denser medium for which the angle of refraction in an optically dense medium is 90 degrees. Okay, so this is the proper definition you must remember. And again, the two conditions again, okay, just mentioned not long ago. So, okay, always have the two conditions when you are explaining. Alright, then we go on, and when we go on to practice, okay, so you did this practice, right? So you know how to find the critical angle given refractive index, quite straightforward, okay, and then you apply, okay, the formula in order to find x. All this is doable. You just have to be very careful. Watch out. Where's the normal? Okay, here's the normal. Okay, this is the boundary. Which is the angle you want? It is not 62. You always measure from the normal. Always measure from normal. So not 62 is actually 28, right? So 28 will be below because the one in medium below, the one in air, x is on top. Okay, and from here you can find x. So this is about refraction. Just be careful. Watch out for the angles. Where are they measuring from? And always remember air on top. Okay, so let's look at an example for total internal reflection. So for example, in this case over here, right, you had a light ray hitting the glass, the prism. Okay, it's a prism at this angle. It will just go straight through, right? It will just go straight through. Why? Because angle incidence is 0 degrees. So here it goes straight through. When it comes here, right here, you have all the answers written for you. You have to check. Okay, you don't take it for granted. Oh, the light ray will come out. There are two possibilities now. Either total internal reflection occur, or yes, the light ray will refract out. So you check. How you check? First thing, go and look for the critical angle. You determine critical angle is 41.8 degrees. Then you use some of your EMAT skills, you find out that here is 45 degrees. So if 45 degrees is bigger than critical angle, you know, okay, it's going to reflect, all of the light is going to reflect at 45 degrees. Okay, so you will come down this way. Then when you explain, okay, you have to say at AC, the two conditions. One, the angle incidence 45 degrees is larger than critical angle which you found. And second condition, that since the light is traveling from the optically denser medium of glass towards air outside, okay, total internal reflection occurs. So I mentioned the two conditions, and then I say what happens, right? And then the light ray, when it hits here, again, is at angle of incidence 0 degrees, it will go straight out, right? So you have a glass block like that, prism like this, no light will come out here, okay? In this case. So what am I trying to tell you? I'm going to try and tell you that you always need to check, okay, whether it's a case of just your usual reflection or is it going to be total internal reflection. Always check the two, okay, when you are doing. Okay, don't assume that, oh, it's always going to be total internal reflection. If the angle is smaller than the critical angle, yes, the light ray will come out. Okay, so always check which case is going to happen. Okay, and then when you ask to explain, remember of what you need to write. Okay, the two conditions. For this one, two conditions, three things: bending away, optical density of medium, and speed of light. Then this one about the angle incidence, larger in critical angle, and is traveling from optically denser to less dense medium. Okay, so always check. Okay, then sometimes you're given something like this, okay, whatever, it may look a bit difficult. The key always is to draw normals. Draw a normal, okay, find out the angles that you're interested in. Okay, what is the angle over here, right? Using your 3-go skills, you find that, oh, okay, 25, 35, then here, this is the sum of angles of triangle, that means here to here is 120, okay, here is clearer, 120. So from the normal, it means this is 30 degrees. So you use your 3-go skills, right? And then if this is 25, this is 65, right? Then you ask yourself, you go and find the critical angle. What is the critical angle of this glass block? They already told you refractive index 1.5. So it's 65 more than critical angle. It is more, then you know the light ray will come out. If it's less, well, the light ray will refract out. Okay, so you always check either case, right? So just practice and be confident. Okay, I'm sure you can do this. Okay, just want to add quickly some applications of total internal reflection. Okay, this is an important application like optical fibers, very useful in these days where we got high-speed internet, right? So what happens? The light, okay, is trapped within the cable, right? So incurs multiple total internal reflection all the way, it reflects, it comes out over here. So you can imagine, since it's traveling at the speed of light, how fast the signal travels. Okay, very fast, right? So what happens is that this fiber has two cores, right? Two layers. So inside will be a higher refractive index, outside will be a lower refractive index. Okay, so that helps set up the idea that the light is trying to travel from optically denser to less dense medium. So that is one condition for field. And then if this angle incidence is more than critical angle, then the light will forever be trapped inside here. Okay, so no one use that is used in optical fibers, in endoscope, all right, in communications, where you transfer information across from one place to another. You can use it in telephone conversations, okay, computer data, right? So, and of course, you also can use it as an endoscopy, right? So to see what's inside your stomach, okay, down your throat, okay, all this is not a very pleasant experience, huh? So what's your advantage of using optical fibers? At least know some advantage, okay, there's less signal loss, okay? They can carry information over very large distances, right? Compared to, let's say you're using electricity, all right, then current running through wire, okay, there will be heat loss, okay, so your signal gets lost much quicker. Okay, then they can carry more what? Data than a copper wire, okay, and they are lighter weight than copper wire, so it's also becoming cheaper. And then of course, because these are optical fibers, they can bend easily, okay, can go around in difficult or dangerous places. Okay, when you explain all this, don't just write one word, faster, okay, do explain properly, like able to carry more data over long distances, okay, so don't just too short in your answers, okay. Then of course there is also the use in glass prisms. You can use it in glass prisms, in a periscope, and so on. So for example, if you were to use your glass prism and put it in this way, in this manner, what happens, you can use it as a periscope, right? So over here, okay, if the object is over here, the light comes from here, it goes straight through this part of the glass prism. Okay, this is a triangle glass prism. So then it hits here, total internal reflection occurs, it will go down, straight down, hits here, draw another normal, and again total internal reflection comes out this way. So the light ray comes out this way. So all the light, okay, is reflected off this glass prism surface down here and towards the eye. So you are able to use it in this manner. Then you can also use it in a camera or even binoculars as well. Okay, so at least you know applications, optical fibers, using in endoscopy and in carrying information, right, communication, and then also for glass prism.